Alright, 1, 2, 1, 2, 1, 2, alright. So, welcome to episodio 5 of Thermo Boys, and today we'll be talking about just a simple turbine. So let's get into it. Okay, so we have water vapor entering an adiabatic and steady state turbine, and it goes in at 4 MPa and 400 degrees Celsius, then leaves at 100 kPa with a quality of 95%. The velocity in the inlet is 15 meters per second, and the area is 0.14 meters squared. So the problem wants us to find the mass flow rate throughout the turbine, and then the work produced by the turbine. So first we have to identify our system. So what's our system here? It's what we're studying, and we're studying the water vapor in the turbine. So let's just write that down. All right, cool. So what's our sketch gonna look like? Well, let's just draw this little turbine here with the inlet. So the water's gonna come in here, in, and the water's gonna come out here, out. But when it goes from here to here, it's gonna produce work, so we're gonna have a work output. And now let's draw our PV diagram. This is gonna show us the relationship between the pressure and the volume. And since we're dealing with agua, we're going to draw our agua curve, and it's going to look like this. And since we're going in as, we first enter as vapor, so we're going to start here at 1, and then we exit with a quality, so it's going to be saturated at 2, this way. Cool. So what are conditions? Our conditions are going to be like the best way we can describe the problem we're dealing with. So we can describe it as an adiabatic and steady state turbine. And since we have mass going through the system, it's going to be open, so it's also an open system. And then we can also describe it as a single stream because we have one inlet and one outlet, so it's single stream. All right, so what are physical laws? The physical laws are going to be dealing with like any equations you're going to use throughout the problem. And I like to write them all out. So first let's just draw this conservation of mass and energy. So we're going to have Q in plus work in equals the sum, or plus the sum, of all the mass flow rates times theta in. So this is just saying that all this stuff going in equals all this stuff going out. So let's try the same thing on the other side, except we're going to use out. Alright, but what does theta mean? Theta is just equal to the enthalpy plus the kinetic energy plus the potential energy. And when you simplify all of this down and you solve for the work out, because that's what it's asking for, you're going to see that the work out equals the mass flow rate times H1 minus H2. And it's also, the question is asking us, what is the mass flow rate? Well, the mass flow rate equation, I'm going to fit it in here. M dot equals the area times the velocity all over little v. And little v is just specific volume. See, am I missing anything? And we're also going to use the quality equation. And the z's can be replaced with any intensive property. So z equals zf plus x, zf, g. F being fluid and G being gas. Alright, so those are our physical laws, everything we're going to be using here. Now let's get into the properties. So the properties, I like to split them into two, like the first scenario and the second scenario, so the in and the out. So let's see, the problem is telling us it goes in at 4 MPa, so we're going to have a P1 equals 4 MPa It also gives us the temperature, which is 400 degrees Celsius. It also gives us the velocity, so let's just write that down. Velocity inlet equals 15 meters per second, and it gives us the area. Alright, and let's see, what about phase 2? It tells us it leads at 100 kPa, and it makes sense because P1 is always going to be greater than P2 in a turbine because that's how turbines work. They work by producing work with a drop in pressure. Otherwise, this wouldn't work. So here we have two intensive properties, so you can look at your thermo tables, which I'm sure you're all very familiar with. And just trust me, I don't have it on me right now, but just trust me. But the properties of water at 4 MPa and 400 degrees Celsius, you're going to go to table A6, and you're going to see that our specific volume is going to be equal to 0.07343, and the units on that is going to be meters cubed per kilogram. Write the internal energy. I like writing everything down just in case I need to use it. So the internal energy is going to be 2920 kilojoules per kilogram, and the enthalpy is going to be 3214.5 kilojoules per kilogram. And this was found using table A6 in your tables. So with this, let's just look at, let's just try to plug stuff in now. So let's start off with, why not the mass flow rate? Let's do it. So m dot equals area times velocity over rho v. And let's see, are we given area? We are, we were given that, so let's plug that in. It was 0.14, and make sure you get your units right. It has to be in meters. So 0.14 times the velocity. What was the velocity? 15. And that's also meters per second, so it's meters. And then all over your rho v, which is specific volume, which we got from our tables. And then that's 0.07343. So if you crunch these numbers real quick, you're going to get that the mass flow rate is 28.6. And that the units on this, you can check them out, but the mass flow rate is how much mass is going through a certain system during a certain time interval. So it's going to be mass over time, which is, we're going to use kilograms per second. So we got our first answer. M dot equals 28.6. Cool. All right. But what about at phase 2? We're going to have to find our work. And how do we do that? Well, make sure that you take note that they're using a quality. So you're going to have to be using the quality equation here. And to do that, we're going to replace these z's with h's because it's an intensive property. And so we're going to have, since we already have x, the quality, let's write x equals 0.95. And then we're going to have hg and or no, not hg, might be hf and hfg. And you're going to get these from table A5. So if you go to the pressure tables on water, you're going to get these values for hf, which is going to be 417.51. And the units on this is going to be kilojoules per kilogram. Always keep track of your units. And then HFG is going to be 2257.5 kilojoules per kilogram. All right, so we're given our quality, and we got these values by using the tables. So now let's try to find what our actual enthalpy is. So let's calculate that here. H equals HF plus X HFG. And let's just plug in our values. So we're going to have H equals 417.51 plus 0.95 25, because that's our quality, times U257.5. Crunch those numbers real quick, and you're going to get that H2 is going to be 2562.135. And the units on that, just like before, kilojoules per kilogram. So now, let's just look at our work equation that you can derive from the conservation of energy. So, we've just found our mass flow rate, so we can say that the work out equals what we just found, 28.6, because that's mass flow rate here. And what's H1? So we're going to look at our phase 1, and we're going to look for our H. Did we write an H value here? Oh no, we didn't, I forgot. But if you look at table A6, you'll see that your H value, oh no, my bad. Yeah, we did. We have an H value right here. So the enthalpy in the inlet is going to be 3214.5. And then what's the enthalpy at the outlet? Well, remember, we got our quality and we plugged it in to see what it actually was, and it's 2562.135. And once you crunch those numbers, you're going to end up the workout equals 656.77, and these are going to be in kilowatts. Cool. So we found our mass flow rate and our workout with a little calculations. It's not that bad. You just have to make sure you catch that quality part, so you use the right enthalpy on phase 2. Yeah, so thank you for watching. Hope that helped out.